Space and time. These two concepts are things that we all have an idea of, but it's hard to pin down an exact definition. We know that space expanded from one point, the Big Bang, but what was outside of space? What did it expand into? How do we define time? We might use constant rates like radioactive decay or the speed of light, but what happens when we experience time at a different rate than other people, or at a different rate than we did in the past? Which time is correct? Our perception or some fixed measurement? And why does it seem to only flow in one direction? On one hand, space and time seem very different. There are 3 dimensions in the space that we can observe: height, width, and depth. We can go in either direction along these dimensions, as well as any direction that is a combination of the 3. On the other hand, time only has one observable dimension, and only one direction in which to travel, from the past, through the present, to the future. How do we rectify these differences? Let's pretend we've somehow developed its technology to stand outside of the passage of time and observe all moments in time. In other words, while it seems like time passes without our ability to change its movement, consider time instead as a 4th dimension, just like the 3 dimensions of our observable space, a dimension we can observe in either direction. If this were the case, we'd see the 4 dimensions together, 3 dimensions of space, 1 layer for each moment in time. We could flip through these layers like a photo album, going back and forth at our ease. Unfortunately, or perhaps fortunately if you're afraid of time travel paradoxes, we only know how to move forward in time at a relatively steady pace. We're nearly certain that the fastest anyone or anything can travel is light speed, approximately 300 million meters per second. A consequence of this is that there are events, specific points in space-time, that can never interact with each other. A diagram called a light cone shows this fact. Imagine 3-dimensional space as a 2-dimensional surface. Every event in the present is contained in this plane. Now suppose we sit at this point in space. As time passes, we have choices as to where we travel in our 3-dimensional space, or in the case of this diagram, along the 2-dimensional plane. However, since we can never go faster than the speed of light, all of the possible events we can be at are contained in this light cone. The edges are only reached when traveling at the speed of light, so we end up somewhere in the middle of this cone. We can draw a similar cone under the plane, symbolizing all of the possible past events that might be affecting us in the present. For example, we are about 8 light minutes away from the sun, so the sun's rays that left 8 minutes ago are just affecting us now. The area outside of this top light cone are all the events that we can never affect, while the area outside of the bottom light cone are all the events that could not affect us in the present. So far we've considered space-time as a Euclidean space, meaning it functions the way we're used to. Straight lines are straight, right angles look like this, and triangles have 180 degrees. However, space is in fact non-Euclidean. Before getting into the havoc that this wreaks on our understanding of space-time, first consider the expansion of the universe. It's been proven by spectra analysis of faraway galaxies that the universe is expanding. In fact, it's accelerating in its expansion. This is known because of the redshift of these spectra. We can detect this shift in the spectra because we know what we expect to get, and can compare that with what we actually get. Though not the same mechanism, it's useful to think of redshift like the Doppler effect. The Doppler effect is what makes the siren of an ambulance sound different depending on what direction it's traveling relative to you. When it's driving towards you, the frequency is higher, and so the pitch sounds higher as well. When it's driving away, the frequency decreases and it sounds lower. The stretching of light is similar, except it's space itself that's doing the stretching. As light travels through the expanding universe, light expands with it, lowering its frequency and therefore shifting the visible spectra towards red light, the visible color with the lowest frequency. If an object is moving away from Earth at a fast enough speed, there's an observable change in this redshift. However, if an object is moving towards Earth, this object has blue shift, or a shift towards higher frequency light. This occurs because as time passes, the object gets closer to Earth, the light takes less time to reach Earth, and space has had less time to stretch that light. Now that we've grasped the concept of an expanding universe, it's time to delve into the curvature of space. This is where we abandon our Euclidean spaces completely. First, let's consider space as a whole. Space is relatively flat, which means that we can use Euclidean mathematics to approximate things. However, adding a bit of a curvature makes for some interesting and completely plausible possibilities. Let's suppose that space is curved like a sphere. What would straight lines look like on this surface? What would a triangle look like? In order to do this, we must imagine the two-dimensional projection that this new three-dimensional surface creates. We can imagine our familiar Euclidean shapes on this projection, and from there, observe what it looks like in our non-Euclidean space. In the case of this partial sphere, a triangle with a vertex at the midpoint and two vertices at the meridian looks fatter than the triangles we're used to. In this space, the angles of a triangle add up to more than 180 degrees. Now consider the flip side, a hyperboloid. A triangle on this surface looks thinner, and accordingly has less than 180 degrees in its angles. A consequence of these curved, straight lines is that if you and I start walking away from one another at a set angle, from one starting point in completely straight lines, our endpoints will be different depending on the space. In Euclidean spaces, we would move away from each other at a consistent pace. In a hyperboloid, the distance between us would accelerate, though we'd still be moving at a constant pace. And on a sphere, we'd eventually reach each other again. The latter can be easily demonstrated by using the Earth. If two people start at the South Pole and start walking due north, but in two different directions, they will each be walking in straight lines, but will both end up at the North Pole. Even the curvature of space isn't a constant. As was recently confirmed by direct observation, objects with mass generate gravitational waves that perpetuate throughout space as a ripple in space-time itself. Gravity can be thought of as the bend in space-time that any object with mass creates. When an object moves, it generates minimal gravitational waves. However, when two objects interact at high speeds in close proximity, like two stars or black holes in a binary system, gravitational waves are generated at a level that we can detect here on Earth with very sensitive equipment. You may have heard about the Ligo Facilities that detected gravitational waves in September of 2015. There are two of these facilities, one at the Hanford site in Washington and the other in Livingston, Louisiana. Both have two perpendicular arms that are 4 kilometers long. There are mirrors at the end of the arms and a splitter mirror. A laser shoots at a beam at the splitter mirror, splitting the beam into two identical streams, which travel down the arms, bounce off of the mirror, then go through a series of reflections between the two mirrors before hitting the splitter mirror and recombining. If there are no gravitational waves detected, then the two beams cancel each other out. However, when gravitational waves pass through the Earth, the length between the mirrors changes a minuscule amount and the beams are offset. Because this change is so small, the multiple reflections between mirrors is necessary to amplify the change. When these beams recombine, they create an interference pattern that can be analyzed. On September 14, 2015, while the Ligo facilities were still in their testing phase, both facilities detected a chirp, the telltale sign of the gravitational waves that result from the rapid revolutions and subsequent combination of two large celestial bodies. In a talk a few days after the public announcement of this discovery, Keith Rouse described the events of that day. He woke up very early in the morning to a series of emails from his coworkers about the potential discovery, wondering if it could be a glitch in the code, which a following email denied. Once they were convinced that this data was correct, they had to figure out whether or not it was planted there by an anonymous testing group. This group's job was to simulate what the facility was supposed to detect in order to test the analysis capabilities of the facility and the scientists working on it. Keith Rouse and his coworkers soon found out that the testing group wasn't even at the stage to be making those kind of tests anyway. The final part of this initial discovery was to confirm that it happened at both facilities and wasn't just a regional anomaly. In fact, the gravitational wave signature was detected at both facilities within 7 milliseconds of each other, a time difference that fit in the expected time interval for the detection of gravitational waves. After its detection, this chirp was analyzed to figure out what caused it and how far away this event was. It's been calculated that these gravitational waves were propagated out from two black holes around 30 times the mass of our Sun and more than 1 billion light years away that were revolving around each other and eventually combined to form one black hole. Space is a weird thing. Even with only our 3 dimensions, the mechanisms of it and its non-Euclidean form gets complicated. Then when you add time into the mix, everything falls to chaos. But every step that we take into the future brings us closer to an understanding of our universe and how it works. Maybe someday, we'll perfect space travel utilizing the curvature of the universe, or extra dimensions we haven't yet observed. Find out if black holes really do lead to other dimensions or pocket universes, and maybe even unlock the secrets of time travel. We've discovered so much, but there's still so far to go.